All right. Before we move into the next example, it's worth taking a moment to talk about these two results at the bottom, Theorem 2 and this first remark. So what we have here is this idea that we know that the curl of a vector field is just another vector field, right? Curl of vector is a vector. So we can think of the curl operation on a vector field as a way of taking an existing vector field and creating a new vector field from it. Okay? So this theorem here is saying that if we are asked to do a surface integral of some vector field f, and if, for instance, we know, so let's say if the curl of some vector field A equals f, then we can say this equal sign. This is the same thing as the surface integral of, well, we can just replace f what f is equal to. F is equal to the curl of some other vector field A. Now, why would we want to do that? Well, because given any surface integral, the double integral over S, f dot ds, then there's not necessarily anything that is connecting this to Stokes' theorem. There's nothing in this box here that screams Stokes' theorem. However, if we know that this vector field f is the curl of some other vector field, as soon as we do this rewriting of f into the curl of this vector field A, this result is now exactly the one side, the double integral side, of Stokes' theorem. So now we could use Stokes' theorem. So right here, this is now Stokes' theorem, to say that this is equal to the line integral around the boundary of S, a dot dr. So in a way, notice here, I mean, this is important. We need this intermediate thing, but if we just put blinders onto this for a minute and just think about this being equal to this, this shows that if our vector field f is the result of a curl of another vector field, then the surface integral over, the flux of a vector field over some surface S, the answer to it actually doesn't even depend on S at all. It only depends on the boundary of S, which is kind of wild. So for instance, let's say we've got a circle, and another circle here, right? I could connect, so we're going to do this two different ways. So, okay, so I'm going to copy that. So option one is maybe our surface does something like this. Right, so this is our surface S. And then we would orient these like this. Okay. So and we have some vector field here. So the line the flux of a vector field over this surface compared with, let's say, take the same two circles, but we have a completely different surface, we could, we could have something maybe we have something like some weird surface. Right? So these are the openings here, here, and here. This is just a hole in the middle of it, like a donut kind of. So the flux of a vector field through this surface here and through this surface here doesn't actually depend on the surface itself. It only depends on these openings, the boundary of S, right? If these are both S, right, two different S's, let's say S and S prime, but they have the same boundary. Boundary of S is just the collection of these three openings. So although S and S prime are different, the boundary of S and S prime are different, or let's say S1 and S2, let's do that, it is actually true that the boundary of S1 equals the boundary of S2, despite S1 and S2 not being equal to one another. Their boundaries are the same, the surfaces are different. And if our vector field is the result of the curl of another vector field, then this tells us that the surface integral over S1 has to be equal to the surface integral over S2. Why? Because of this assumption here. If F is the curl of some other vector field, then the result is surface independence. Surface independence. Okay. So that's a pretty cool thing. And honestly, this is essentially, it should sound very familiar. It should be, hopefully it's kind of interesting and kind of wild. I think that's the best part of math. But this should hopefully also be a little bit familiar. Remember that with conservative vector fields, right? For conservative fields, remember, what does it mean for a vector field to be conservative? I.e. that the vector field F is the result of the gradient of some scalar function. So if a vector field is conservative, that means it's the gradient of some F, then the line integral around the boundary, the line integral over a path C, f dot dr, does not depend on the path itself. It only depends on the endpoints of the path. So in a way, this right here is the next dimension higher version of the fundamental theorem for conservative vector fields. This tells us that this integral over C, let me go back a second here. This circle does not need to be there. I'm sorry. Let's take that circle off. I didn't mean to imply that this path had to be closed path. Let's just leave this like that. So this right here shows that the result to this line integral is independent of the path C. It only depends on the endpoints of the path C. You could have any path connecting these two dots, and they would all have the same answer. Similarly, you can have the same two openings, and no matter what your surface looks like, you get the same answer. So here we have a result about path independence. Here we have a result about surface independence. And what do we know about the fundamental theorem for conservative vector fields? That if our path is actually closed, and f is the gradient of some scalar function, then this is 0. Well, same thing happens down here. If our surface is closed, so for instance, like the surface of a sphere, there's no holes, right? There's no edges. There's no edges. You can't go from the outside into the sphere unless you poke it or puncture it. So the sphere is an example of a closed surface. It completely separates 3 dimensions, in this case, into one area and an area within, or a volume outside and a volume within. Then the boundary of S is empty. There's no bound. I mean, there is a boundary. It's just empty. And therefore, we get 0. So specific to this theorem too, let's erase this conservative vector field stuff for now. Down here, we talk about this A. This is called a vector potential for F. Remember, with conservative vector fields, we would say that if F is the gradient of some scalar function, we'd call this function F a potential function. And then there were a couple times that I probably said, okay, yeah, we'll just call it a potential, but really, in particular, this is called a scalar potential function. Why? Well, one, F is a scalar function. It's a scalar quantity, so that makes sense. Well, the other reason is to distinguish it from A, because we can have a vector field F. F could be the gradient of some scalar function, or F could be the curl of some vector potential function. Excuse me. So that's what we have. And remember, if you're given F, so if the curl of F equals the 0 vector, then what does this tell us? This tells us that there exists a scalar function such that the gradient of little f equals big F. Well, there's a similar notion for this case. If the divergence of your vector field is 0, then there exists a vector field A such that the curl of A equals F. And what's completely outside the scope of this course is something really cool, and it is a really neat symmetry that happens. So in manifold theory, so basically taking the calculus that you're learning here and extending it to working on any dimension, not just Euclidean space, but any sort of space, doing calculus on things where you wouldn't even think calculus applies, so 20-dimensional non-Euclidean manifolds, and weird spaces like that, there's this nice little result. There's a version of the derivative called the exterior derivative. And the exterior derivative is a way of taking things that live in a certain set, a certain space, called zero forms. So this exterior derivative d is a way of taking something that's a 0 form and turning it into something that is a 1 form. And then you can do it again by taking it into a 2 form and then taking it into a 3 form. What's neat here is that what we're used to what we're used to here is this nice symmetry here. So essentially what we can think of here as we can think of this as scalar functions taking the derivative of it would give us a vector field. So a vector, I'll put in parentheses field. And then we can convert a vector field into another vector field. And we can apply d again. I forgot to write that last d. We can do that again to get a scalar. So what is this operation? It's the same function, just applied in different ways. Well, what we end up finding here is that there is this correspondence where there is, what we teach you is the gradient. And then we teach you that there is this thing called the curl. And then there is this thing called divergence. So for us, this is a map basically from real numbers to 3 dimensions to 3 dimensions back to 1 dimension. So in manifold theory, what appears to you guys as very different things, gradient, curl, and divergence, they actually all are the same exact function. It's exactly the same thing. So they look very different, and then all semester I've highlighted these coincidences and these similarities between things. And they're not coincidences. These are all just different manifestations of the same thing, but in a very specific setting. What's also neat here is the fact that this exterior derivative, that if you act on something with it twice, no matter what you act on it, if you act on something, omega, if you act on it twice with the exterior derivative, you'll get 0. And you can verify this. Remember that remember that a vector field, so f is conservative if it is the result of the gradient of some scalar function. Okay? And remember, how are you supposed to check if this field's conservative? What are you supposed to do? Well, we tell you, take the curl of f. So, we tell you that if the curl of f equals the 0 vector, then f is conservative. Well, notice here that if f actually is conservative, then that means this f is really the gradient of f, which is really sort of saying this. And if the gradient, if this operator is really just a manifestation of this exterior derivative, then this is no different than a manifestation of the fact that acting on something twice with the exterior derivative gives you 0. And that's exactly why we can check if a vector field, right, if f is the curl of A, then the divergence of f should be 0. Why? Well, if f in fact is the curl of A, then this is saying effectively this. I mean, it's not, the notation's a little bit wonky here, but this is effectively another manifestation of this idea. So it's a very interesting set of symmetries here. But again, that little bit there is well outside the scope of this class. It's just something that I find to be very interesting.